Good morning, my name is Sharon. I am from CACIML Section C. So today my topic is matrix-based Markov chain modeling for reliability prediction in engineering systems. Matrix-based Markov chain modeling reliability prediction in engineering. This presentation explores the powerful application of matrix-based Markov chain modeling as a sophisticated tool for predicting reliability in complex engineering systems. Uh, we will live into the fundamental concepts, practical application, and significant benefits this methodology offers in ensuring systems longevity and operational excellence. Understanding and implementing these models can significantly ensure the design, maintenance, and overall resilience of modern engineering infrastructure. So, why reliability matters? The cost of failure. So here are 3 points. First one is financial losses. Billions lost annually due to equipment failure and system downtime across various industries. And the second one is reputation erosion. Customer dissatisfaction and brand evolution resulting from unstable services. And the third one is safety hazards. Crucial failures can lead to catastrophic accidents and endanger personnel. And introduction to Markov chain, states, transitions, and probabilities. Markov chains provide a mathematical framework for modeling systems that transition between different states over time, where the future depends only on the current state, not on the sequence of events that preceded it. The memoryless property is fundamental to their utility in reliability analysis. States represents the possible conditions of a system or compound. Transitions, movements between these states occurring at specific intervals or rates. Probabilities quantify the likelihood of transition from one state to another. Understanding this core concept is crucial for constructing an accurate Markov model that can efficiently represent the behavior of complex engineering systems under various operational conditions. Applying Markov chain to engineering systems, compounds as states. In the context of engineering reliability, each compound or subsystem within a large system can be viewed or occupying a particular state. These states reflect its functional condition ranging from fully operated to various degrees of regraduation or complete failure. Operational state. The compound functions as indeed contributing to overall system performance. Degraded state. The component's performance is reduced but is uh, still partially functions, potentially impacting system efficiency. Failed system. The compound is entirely non-functional, leading to system failure or requiring immediate intervention. And repair state. The component is undergoing maintenance or repair until a failure, moving towards an operational state. By defining these states and the possible transitions between them, engineering can create a comprehensive model that captures the dynamic behavior of complex systems, providing a detailed understanding of potential failure models and a recovery process. So, component state. Each component's condition defines a specific state within the Markov model. Failure models. Identification of various ways a component can fail or degrade. building the transition matrix, quantifying failure and repair rates. The heart of Markov chain modeling is its transition matrix. This matrix encapsulates all the probabilities of moving from one state to another within a given time interval. For reliability analysis, this involves quantifying both failure rates and repair rates. So, what is failure rates? The probability per unit time that an operational component will transition to a degrade or failed state. These are often derived from historical data or accelerated live testing. Uh, Repair rates. The probability per unit time that a degraded or failed component will be successfully repaired and returned to an operational state. These rates depend on maintenance strategies, resource availability, and component complexity. Accurately populating this matrix is crucial. It requires robust data collection, statistical analysis, and often expert judgment to ensure the model reflects real-world system behavior. Small inaccuracies here can lead to significant reliability predictions. So here they give a equation solving for steady state probabilities predicting long-term reliability. Once the transition matrix is established, the next crucial step is to solve for the steady state probabilities. The probabilities represent the long-term proportion of time the system or its components will spend in each defined state, assuming the state operates indefinitely without external changes. So here they give 3 points. First one is formulate equations. Set up a system of linear equations using the transition matrix where the probability of being in a state at the next step equals the sum of probabilities of transitioning into that state from all other states. Second one is solve for pi vector. Solve the system of equations for the vector pi which contains the steady state properties of each state. This often involves techniques from linear algebra. And third one is interrupt results. The resulting probabilities indicates the long run availability, reliability and expected downtime of the system. For insurance, the steady state probability of being is in operational state directly correlates with long-term system availability. Case study. Reliability of a complex power grid. Consider a power grid comprising multiple generation units, transmission lines, and contribution networks. Each of these elements can operate degradable or fail. Markov chain can model can efficiently analyze the grid's overall reliability. Defining states. States could include full capacity, partial outage, or major outage recover mode. Transition rates. Based on historical data of component failures, example transformer malfunctions, line breaks, and repair times. Scenario analysis. Advantages of this approach: dynamic analysis and maintenance optimization. Matrix-based Markov chain modeling offers several significant advantages over traditional reliability assessments methods, particularly for dynamic and complex systems. Dynamic behavior captures the time-dependent evolution of system states, offering insights into reliability over varying periods, not just static snapshots. Maintenance optimization helps determine optimal maintenance schedules, balance the cost of preventive maintenance against the risks and cost of failures. And interdependency modeling efficiently models the complex interdependencies between various components and the subsystems, undertaking how one failure can cascade. And risk assignment. Challenges and limitations, data requirement for modeling, model complexity, assumption of memory loss, parameter estimation errors, and model complexity. Key takeaways and future direction in enhancing system resilience, predictive power, strategic maintenance, and risk mitigation. Thank you.